and now I will tell you what is the actual difference between these three problems and why these three problems can be considered as different setups within sequential decision making. Okay, and for that, the key point to note is, yes, there is feedback in all these three problems, but what is the nature of feedback is the question, right? So, the nature of feedback. Now, what do I mean by nature of feedback? I will tell you now, right. So, now let us look at the stock market prediction problem. So, what was the problem again? So, every morning I get expert advice to predict or not in a stock. I make a decision. At the end of the day, I am told whether my decision is correct or not. I get the feedback whether my investment decision was a good decision or a bad decision, right. So, if I decided to invest and the stock market went down, then it is a bad decision, and otherwise, right. So, there are 4 possibilities there. Now, that is the feedback that I get. Now, what did I rely on to make my decision? I relied on the expert advice, and there are 100 experts. Some of them said yes, invest, some of them said no, don't invest. But I, as an algorithm, somehow looked at these values and then I decided to invest or not invest. Now, I get the feedback whether my investment decision was right or not. Now, let us say I could have chosen to go with any of the experts' answer. I have 100 experts, 100 friends. Let us say on this particular day, I decided to follow the 53rd expert for whatever reason. Let us say my algorithm said go follow 53rd expert, which means that if the 53rd expert said invest, I would invest. If the 53rd expert said don't invest, I will not invest. Now, the feedback that I get will tell me whether my decision was correct or wrong. Now, the careful thing to notice here is that the feedback is telling me whether my decision is correct or not, but not only that, it is also telling me whether the first expert was correct or not. It is also telling me whether the second expert was correct or not. It is also telling me whether the 100th expert was correct or not, right. So, each expert said something, but I decided to follow only the 53rd expert. But the feedback that I get is not just for the 53rd expert, it is for all experts, because let us say the 53rd expert said yes, so I decided to invest and the stock market went up. That is a good feedback for me, right. So, it is a good decision for me. But then let us say the 54th expert said no, I did not follow the 54th expert, but the feedback that I get is also telling me something about whether the 54th expert made a mistake or did not make a mistake. Same with 55th expert, same with all the experts, right. So, what I am getting is, I am getting feedback for the expert I followed and also for the experts I did not follow. In other words, I am getting full feedback, and this is called as a full information setting, right. Full information setting. That is, again, just to reiterate, the feedback is not just for the decision I make, but also for the all other decisions I could have made, but I did not make, right. So, I could have followed any of the experts, but I chose the 53rd expert. So, I am getting the feedback for the 53rd expert, and I will suffer based on the 53rd expert's decision. But I am also having the extra information about whether the other experts were correct or not. So, that is what I mean by full information setting. Now, this will become even more clearer when we contrast this with, let us say, the healthcare example, healthcare problem. Now, what happens in this case? Again, just to summarize what the problem was, I have 4 tablets. I need to decide which tablet to give to the patient. Now, I choose one tablet. Let us say I chose the first tablet, T1, and gave it to the patient. The patient goes to home, eats tablet 1, and then at the end reports whether tablet 1 worked for him or her or not. So, the feedback that I am getting is for tablet 1. Now, I could have chosen to give tablet 2 to the patient, tablet 3 to the patient or tablet 4 to the patient, but I did not. My algorithm, for whatever reason, chose tablet 1. So, I chose tablet 1, the patient took only tablet 1 and is reporting the feedback for tablet 1. Now, there are other possibilities I could have chosen, but I did not choose. And for these possibilities, I do not know what would have happened had I given these tablets to this patient. You see, so I am giving a certain tablet to the patient and I am only told whether that tablet works or not, obviously, because the patient only took that tablet, which means I get feedback only for the decision that I took. I do not have feedback for the decisions I could have taken, but I did not take, right. So, this setting is called as partial information setting because I am getting feedback only for the decision I make, but not for the decisions that I could have made, but I did not make in this particular round, right. So, this is what is called as a partial information setting. And that's an important point to note. Now, the third question is robot navigation problem. Now, I want all of you to think about whether this is full information or partial information. Now, this is a good place to pause and think whether the robot navigation problem, first of all, is a full information problem or a partial information problem. If you want a little bit more detail, let me summarize the problem. Again, the robot is in some grid and now it has 4 possible decisions that it can make, either move front, back, left or right. And now it takes a decision and it receives some feedback. Now, is this a full information setting or a partial information setting? Now, I am sure all of you have figured this out correctly. Yes, it is a partial information setting. Why? Because the robot is getting feedback only for the decision that it took. If the robot moves forward, well, either there is no obstacle and then it managed to move forward by 1 unit and that is good feedback, or it went and banged into a, let us say, an obstacle, and that is bad feedback. Whatever it is, good or bad, the feedback is only for the decision that the robot made, which is to move 1 step forward. I do not know, rather the robot does not know what would have happened in that round had the robot chosen to move to the right or to the left or back. So, it had 4 possibilities. It made a choice to pick one of these possibilities and it is receiving feedback only for the possibility that it chose and it does not receive for the other possibilities. So, it is partial information. Now, then the question comes, well, is the robot navigation problem same as the healthcare problem? Because both are partial information, right. So, let me first write down that this is partial information. It is a partial information setting because you are only receiving feedback for the decision that you took, not for the other decisions you could have taken, but you did not take. Now, the question is this same then as the healthcare problem? That is a very subtle question to ask and think about. I will let you pause and think about to see if you can figure out if there is any difference between the robot problem and the healthcare problem in terms of the setting. Now, let me tell you what might be a very subtle but key difference. The difference is as follows. Yes, in both the cases, I get feedback only for the decision I took, but not for the decision I could have taken, but I did not take. That is same for both. I am only getting feedback for the tablet that I chose in the healthcare problem. I am only getting feedback for the direction I chose to move in the robot navigation problem. Now, in the robot navigation problem, something extra happens. Let us look at this setup, right. So, this was the grid that I had earlier. Well, the obstacles I might draw it differently, does not matter. I am just trying to illustrate a point here. Let us say the robot is at this position, right. So, at a particular round, and now let me add some obstacles here, 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 right. and now let us say the robot in this round decides to move forward, right. So, it makes the forward move. Now, is the forward move a good move or a bad move for the robot in this scenario? Well, it is obviously a good move because it is not banging against any obstacle. So, the robot let us say makes a forward move, and now in the next round, this is in round t, in round t plus 1 the robot is now in this position. Now, what happens? Well, earlier moving forward was a good decision. So, at round t, now at round t plus 1 is moving forward a good decision? Well, let us say if the robot decided that, well, I decided to move forward in the previous round and that gave me good feedback, positive feedback. So, I will think of moving forward as a good thing to do. And then if it tries it out now, what will happen? Well, if it tries it out now, okay, if it tries to move forward at this location, now it is going to hit an obstacle. So, what does that mean? Does that mean moving forward is a bad idea? Or because in the previous round moving forward was a good idea, is moving forward a good idea? What is the answer to that? Well, the answer is it depends. It depends on where the robot is, right. So, if the robot is in this location, then moving forward is a good idea, whereas if the robot is in this location, moving forward is a bad idea. So, though the decisions that the robot can take are exactly the same, which is moving forward, left, right or back, now depending on the state of the world the robot is in, when I say state of the world, it means in this particular example, depending on which grid the robot is in, the same decision might be good in one grid, whereas it might be bad in another grid, right. So, what is happening is, when the robot made a decision in this bottom location to move forward, two things have happened. One is you got a feedback, the robot got a feedback that it is a good decision. Now, what it also gets as feedback, or what happens after it gets the feedback, is that it has actually moved forward, which means that the state of the world has now changed. Now, it has to learn whether moving forward is a good thing or moving left is a good thing, again entirely in a new way, because the state of the world has changed. So, what happens in this situation is that you get partial information as feedback. So, it is a partial information setting, yes, but with an extra condition that the state also changes, right. So, with state change, right. So, which means that depending on which state of the world you are in, the robot now has to learn whether it should move to the right, left, back or forward. Whereas, in the previous healthcare problem, there is no state change. The tablet is either good or bad, right. So, it is good for certain percentage of people, that is the ground truth, right, and you do not know that ground truth. Now, if you prescribe a tablet to somebody and then that person gives you feedback whether that tablet worked or not, yes, that is a partial information because I do not know about how the other tablets would have worked in this round, that is true, but that does not affect the goodness of the tablet. There is no world, the world does not change, right. So, the tablet is going to remain with the same goodness in the next round also. Whether it is good or bad, that is not going to change in the next round, it is going to be the same. Whereas, in the robot case, because the state of the world changes, the possible decisions that it can make, the goodness of the decisions can change, because in one place moving forward might be a good idea, another place moving forward might be a bad idea. Whereas, no matter which day, either the tablet works or the tablet does not work. It works with certain efficacy, it does not work with certain efficacy. 90% of the time it works, 10% of the time it does not work. Does not does not matter whether it is a Monday or a Tuesday or a Wednesday. It's the tablet is the same thing. The state of the world does not change with respect to the tablet. Whereas in the robot's case it does, right. So, and that is the subtle difference. So, these three are three broad important settings for the problem of sequential decision making, and depending on the feedback that one receives, these problems can be categorized as either full information or partial information or partial information with state change. Okay. And now if you do a proper data science course, right, so you will talk about more subtleties in each of these headings. How can you solve full information problems, how can you solve partial information, and the third one with state change as well. As you can see, the full information should be slightly easier to solve because you have more information at your hand to solve the problem. Partial information might be slightly harder, and if state also changes, it's going to be even more harder, right. So, these information settings also have some names. Sometimes this setting is called the online learning setting. I am just going to give these names. Again, if you take a full-fledged course, they will understand why these names and etc. So, the second thing, partial information setting, is sometimes called as it's a weird name, and I am not going to bother to explain why this name in this workshop, but again, as you said, you can, if you take a full-fledged course, I mean if you do a data science degree, you will definitely encounter these problems there. Right? So, it's called the multi-arm bandit setting. And the third one, which is partial information setting with state change, that is sometimes called as the reinforcement learning setting. Right. So, these are three main types of sequential decision making problems. Now, as I promised, we have to talk about some simple algorithms at least, so that you get a feel for how to solve these problems. We have just said what the problem is so far and what are the different types of problems, and we have identified what is the difference between each of these types. Now, just to get a feel for the problem itself, we will take one simple problem among these three and then try to develop an algorithm that will work for that problem under some setting. That is our goal for the next part of this lecture. For that purpose, what I am going to do is I am going to take the stock market prediction problem, and then we are going to solve it in a special case. Okay.